Now we shall look at part B of fluid machines and machinery lab, that is 18 MEL 57. This basically part B consists of major applications like turbines. One is Kaplan turbine, Francis turbine, Pelton turbine, or finding the efficiency of the pump or finding the efficiency of a air compressor. So we have got all the 5 equipments. So one by one we will study. This in your examination, this is asked for 50 marks, whereas the part A, whatever we have discussed earlier, those are for 30 marks. So totally 80 plus 20 for the Viva, it will have 100 marks. We divided this way. So I will explain that this experiment setup, what you see, is for the reaction turbine. Turbines are two types. One is the Pelton wheel, the impact turbine, or the reaction turbine. And the turbines are used basically, they are rotating devices, dynamically rotating devices, which are used to produce electricity. So the energy of the water is converted into mechanical energy, and that mechanical energy is converted into finally electrical energy. You might have seen wind turbines. When the wind hits, the wind turbine rotates and they generate electricity. So these hydraulic turbines you have found in dam, like for here you have got that Kadra dam, Supa dam, and fortunately we have visited those dams, and we have seen that both the dams, Kadra dam and Supa dam, have reaction turbine. One has got the Kaplan and another has the Francis turbine. So how the selection of turbine takes place? Because the water will have different heads. Some you can call low head up to 50 meters, then 50 to 100 meters we can call it as a medium head, and beyond 100 meters we can call it as high head. So what is the head? Head means the dam height and the turbine, center of the turbine. Whatever is the head, that is what the head. And that head varies depending on the location. Like Kadra you have got a low head, whereas Supa you have got a medium head. So the selection of turbine is very simple. For low heads like less than 50, 30, 40 meter head, Kaplan turbine is the best suited turbine. This Kaplan turbine is the best suited turbine for low heads, where the head is low but the discharge will be more. Water supply will be high. That is for Kaplan turbine, that is a reaction turbine. One more reaction turbine is Francis turbine. This is for medium head, say 50 meters to 100 meters of head of water, and the discharge is also medium. This is a reaction turbine. Both are reaction turbine. And when the head is very high, more than 100 meters, say 150, 200 meters and all, then we use the Pelton wheel, which is used for very high heads and low discharge. So these are the 3 types of turbine, and this is a classification how you use based on the head as well as discharge. Discharge means quantity of water required to run the turbine. So now this discussion we will have for this reaction turbines. I will explain both of them. Both of them have the same experimental setup. Like this is a tank. Okay, here I don't have a dam. I don't have a dam. So what we have done, we have taken a tank. Okay. So this tank is at a ground level. So to increase the pressure, what I am doing, I have got a motor and I have got a pump. Okay. So I will start the pump, and the water is taken from this, and this is the valve, main valve. From here the water is pumped. Okay. Now to find out what is the amount of water flowing, I need to measure the water flow rate. So this is a venturimeter, like this. You can see the venturimeter 3 components, converging, throat, and this is a diverging part. And you have got the 2 pressure gauges here to find out the P1 and P2, so that you can find out the flow rate of passing through this. And this output, this is a common output, is connected to Kaplan turbine as well as Francis turbine, and there is a valve here, you can see here. This inline means it is on. If you bring it horizontally means it is off. Suppose I want to take Kaplan turbine now, so I will put this in half. So now the water is only flowing to the Kaplan turbine. Okay. And here you see that this is the pressure, inlet pressure to the turbine. And here you have got the scroll. This is the Kaplan turbine basically. The scroll passing casing you can see. There is a runner, and then this water again goes back. This is known as a tail race. because the pressure after this runner is very low. Sometimes it can be below atmospheric. That is why you have got a draft tube with a circular cross section and increasing cross section, so that the pressure is increased and the water is discharged. Here what we are doing, first of all we are measuring the flow rate of water, then the inlet pressure to the turbine, and this when the water is flowing on the turbine, the turbine blades are rotating, and that is connected to the, you can come and see here, this is connected to the shaft here, and the shaft is connected to a belt. You can see one single belt is V belt is there, and below the V belt there is a electrical generator that generates the electricity. Okay, that generates the electricity. So this water power is converted to mechanical power. Mechanical power is converted to electricity, and that electricity we have got. You can see we have got the bulbs here. We have got the bulbs. So these are the load. These are the basically load 160 watt each, and these are the switches for the different loads. Okay, now as we have got both Kaplan as well as Francis turbine, now here the switch this F means if I bring it here to F, this select the Francis turbine, K is for Kaplan turbine. Similarly the switch, toggle switch is there, F is for Francis. Now suppose I want to say Kaplan, means I start here Kaplan, I will bring it here, now it is Kaplan turbine ke liye. This is the starting the main pump, this is the starter. This is the RPM, to find out the RPM of the turbine at what RPM it is rotating. This is the voltmeter, digital voltmeter, and this is the digital ammeter. So V into I is the power developed, and this is the load. The whatever electricity is generated, it is dissipated into the atmosphere through the electric bulbs. Okay, so now we will start. For 1 minute, I will just show you how it works. So now Kaplan will start. First we will start Kaplan. I start about Kaplan.
Francis.
ಅದು ಇದು ಬಂದು ಮಾಡ್ರಿ Francis is off. Sorry, Kaplan is off. Francis is off. Okay.
Yes. We shall look at the second reaction turbine, that is known as Francis turbine. Actually, these are all scientists. Kaplan is a scientist, Francis is a scientist, the Pelton is a scientist. They came out with these turbines way back in some 1800s, and that is why this name of turbines are named after them. So again, this Kaplan Francis turbine is a reaction turbine. It's a medium head, medium discharge turbine. Here you have got the guide vanes. You can control this. This is a, you can see here, when this is guide vanes, you can see the movement of these guide vanes. You can see this guide vanes are moving when I operate this valve. Okay, the experimental setup is same simple. We don't have a dam, so what I have done, I have taken a water tank. I have got a water pump here. This is a motor and this is a pump. This is the valve. So when I start the valve, the water flows like this. The flow, this is a venturimeter, red color venturimeter with the converging zone, throat as well as diverging zone, and these are the two pressure gauges to find out the pressure, so that I can make out the flow of water flowing through there. And here the water will come. So this is the water inlet pressure to the Francis turbine. This is the valve. This valve is up inline, means water will be flowing to this. This is the guide vanes. I can control the flow rate through this. Okay, and the outlet is connected. This is a vacuum gauge, and this is the draft tube. As I told earlier, draft tube, because the pressure which is coming out is lower than atmospheric, so you have a drop depth of increasing cross section, so the water is discharged back to the tail race. Again, then this is called as a tail race. Okay, the pipe from where the water comes to the turbines, that is known as penstock basically. That is known as penstock. And in this experimental setup, what we have done, this is the Francis turbine. So now water I am supplying to the turbine. Okay, when I supply the water to the turbine rotates. So the energy is converted into mechanical energy, rotation of this runner. And this mechanical energy, you can please come here, you can see there is a bed drive. So here you got a generator. So this generator generates electricity here. So the water energy, hydraulic energy is converted to mechanical energy. Mechanical energy is converted into electrical energy. That electrical energy, to dissipate that, we have got a load here. You can see the load 60 watt bulbs are there. This is the electrical load. So each one is 60 watts. Okay. So we will have different loading like 2 bulbs at a time. So 120 watts, 240 watts, 360 watts. Okay. And again, this is the main switch to start the pump. This is a rotary switch, so that now Francis and coupler. Now I want to talk about Francis, so I bring it to F. This is the toggle switch F. This stands for Francis here because this setup is having both Francis as well as coupler and turbine testing. This is a digital RPM meter. You can see this stroboscope here. This will tell the RPM. This is shown here RPM. Voltmeter, digital voltmeter is there, and this is the digital ammeter. Okay. So V into I will give the power developed, and this is the load. So for 1 minute we will start this Francis turbine also. We will see how it sounds. You can see this. We shall look at the third type of turbine, that is the Pelton wheel. Pelton wheel is basically an impulse turbine. We'll study this turbine in detail now. And this turbine is used basically where the heads of water are beyond 100 meters and the discharge is low. For high heads and low discharge, Pelton wheel is used. Here the water hydraulic energy is converted to kinetic energy. You have got a nozzle. Okay. And then the water hits the cups. You can see the hemispherical cups, and this turbine rotates. And here earlier we had a electrical generator. Here we have got a brake dynamometer. So we will find out the power generated by using the brake dynamometer. We don't have electrical dynamometer here. Like here we had a generator in the reaction turbines. So the experimental setup, basically what are we doing with these turbines? We are only seeing the efficiency first. First efficiency means what is the energy contained in the water and how much energy of the water we are able to convert into mechanical energy or electrical energy. Okay, so that conversion ratio we are going to see. That is performance of the turbines. That is power developed divided by theoretical power, what it can develop based on the hydraulic energy input. So this is a tank. Again, we don't have a dam, so we have a tank here. And this tank is connected to a pump. You can see here the pump is motor and pump is there, and the priming element is there for the pump here. So I will start the pump. The water flows from the pump here. This is a valve. Again, to measure the water flow rate, you have got a venturimeter with the pressure gauges at the inlet as well as the throat. Okay. So if you find the two pressures, and based on that you can find out the flow rate. And this is the inlet pressure which is coming to the Pelton wheel, and this handle is used to move the nozzle. We can increase or decrease the nozzle here, and the Pelton wheel rotates. And if you come here, you can see this is the belt diameter. Basically, this is a belt diameter. You have got two spring loads, one here and the other spring load here. So and this belt, because of this friction, it gets heated up. So there will be a small water supply also to cool the drum basically. And the water, excess water, if it is there, it will flow through this tank and go back to the main tank. This is the experimental setup. Like once again I say, this is the main tank, and from this main tank you have got this suction tube. It is connected to the pump. This is a pump and this is a motor, electrical motor. So this pump, the water comes here. You have got a valve here, and the water comes to the venturimeter to measure the flow rate, and it comes to this pipe. This pipe in a diameter of this main pipe is known as a penstock. Basically, it's a very big pipe, penstock. And from here there is a valve. This is to control the nozzle. You can control the rate, flow rate, increase or decrease the flow rate. And this blue is the you can see the Pelton wheel. This is known as a Pelton. It has got like two conical shape. This one cups. So the water will hit at the center and split like this, and it will rotate. This will spin at very high RPM. So this is the experimental setup for pendulum wheel, and we are going to find out the efficiency of the Pelton wheel, like we have found out in for reaction turbine, like the Kaplan turbine and Francis turbine. Here also we are going to find out the efficiency of the turbine, and we are going to plot the characteristic curves. Okay, thank you. We shall look at the performance like centrifugal pump test rig. Okay, this is a centrifugal pump test rig, and here this is a centrifugal pump. You can see this green part is a centrifugal pump made by Kirloskar Brothers. Okay, this is a 2900 RPM pump. Okay, and the head is 21 to 25 meters. Okay, this is the centrifugal pump, and we are going to find out the efficiency of this pump. So this is a main tank. Okay, this is a main tank, and this suction pipe to the pump, and the water comes here, and this is a delivery pipe which is going into this tank. So this is my measuring tank. So this is a measuring tank, and here I have got a scale attached to this, and I will close this valve so that I will find out the time required in seconds for 10 centimeter rise in water level here. This is the experimental setup, and now you can see I can vary the speed of the pump. So you can see minimum and maximum here. So this is a RPM, digital RPM meter. You will find out you will get the various RPM, like it was at 2900. So I can start from 1500, say 1800, 2100. So different 4 to 5 steps to facilitate plotting in graph. So this is the RPM meter. I can change the RPM. Okay, one thing. And this is a vacuum pressure at the suction, and this is a delivery pressure. This is a delivery pressure, and that is a vacuum pressure. These are two pressure gauges here. And this is the electrical energy. Whatever this pump is generating, that energy is converted to electrical energy. And here you can see this is a energy meter, basically single phase 2-wire energy meter. And this is the DC motor and generator which drives the pump. This is a DC generator. So because it is DC, I am able to easily vary the speed here and find out. So what I will do, I will start the pump. Okay, I say at 1500 RPM. I will take the readings of the suction pressure, delivery pressure, and the power produced. Then I will increase it, say, to 1800. Again, I will see the digital RPM. Then I will see the power produced and these readings of suction and delivery pressure. So this way, I will take some 4-5 readings, and I will plot the efficiency of the centrifugal pump with respect to the speed. And this is how we find out that, and this is for priming. When I want to start the pump,
So there will be air in this. So I will put water here so that I can prime the pump. This is the experimental setup, and this is a valve, so I can control the various flow rate I can control. And this is a measuring tank where I want to scale, and I will take the time required for 10 cc rise. So these dimensions of the tank are known, so I can find out the discharge. So this scale and this tank is meant to find out the discharge flow rate. Okay. So this is how we find out the performance of a centrifugal pump. I hope this experiment is clear. Thank you.